Spanish flu, it lasted 18 to 24 months before the whole thing was over. So I think that's what we've got to look forward to. And it's been hard on everybody, and it continues to be hard on everybody, but at least let's try not to kill any more people. Or if you get this disease, it can wreck your body. And that's really hard. Ooh, it's time to start. Okay.
Good morning, Dr. Kennedy. I just had a quick question.
Okay.
Did you happen to post the tutoring links on the course webpage on Blackboard?
Yes.
Oh, okay.
Yeah.
Somebody was asking about the tutoring schedule and all that.
It's posted there. Okay. There are a lot of things posted there at this point.
Okay.
They're posted in more or less chronological order. So, well, that makes it easy to find the notes and the recordings, but the tutoring lab schedule, well, it was posted probably a week after it came out. And so that would be like the second week of class. So you'll have to go back a little bit, but it is there.
Okay.
Okay.
Thanks.
Okay. Let's see. Let's start class. Is there one more? And let's make sure. Okay, good. Going to my screen. All right. And that was Mr. Levy's question, which I hope makes that more clear. Let's do ours. Okay, we started talking about the differentiation rules. And let me remind you, this is not for your homework tomorrow. That's due tomorrow. For the homework due tomorrow, you are to only use that definition of derivative, which means the limit definition. One of those two limits. You're to compute your derivatives using only that one of those two definitions, okay? So this is material that I'm talking about now that will not be on the first exam. Not only will it not be on the first exam or on your homework tomorrow, you will not get credit for what you do tomorrow if you use these rules. Because the rules are valid for a reason. They're valid because of that definition, which is why I want you to understand it. Okay, enough sermonizing. Let's go. Okay, we've already proved that if you have a function that's a constant, which means the graph of the function is a horizontal line, okay, its derivative is 0. That's because there's no change. If you have well, we proved it actually. So let's see, it changed the color here. The graph of f of x equal to c is something like that blue line where, okay, c is whatever that number is. That there's no change. I mean, in that graph, right? You look at a number here, you get c. You look at a number over here, you get c. You look at a number there, f of that number is still c. There's no change. That's why the derivative is 0. Okay, the derivative is telling you about a rate of change. When we proved some cases of this next result yesterday and the day before. If you have f of x is x to the n, that's what you usually call a power function, and n is fixed. N is a fixed real number, and you do have to worry about sometimes where f is defined. because you don't have a derivative where the function is not defined, that's for sure. But as long as it's defined, f prime of x is n times x to the n minus 1, except maybe at the end point of the domain. But as long as the derivative exists, that's what it is. Okay, and we proved also that if you take the derivative of a constant times a function, that's just equal to the constant times the derivative of the function. In other words, you can pull a constant out when you're doing computing a derivative. A constant that's multiplied by the function can just come out of the whole thing. All right, so we proved we proved a couple of cases of this. We didn't prove that in its entirety. In fact, in the most general case, it's beyond us at this point. But the next rule, the derivative of the sum of two functions is the sum of the derivatives. Okay, and remember, we have, well, already many ways of denoting the derivative. F prime, for f a function, f prime is one way. You can also write this capital D of f of x, means the same thing, or you can write df dx. Those three expressions all mean the same thing. Okay, so let's prove this result about the sums. Okay, and this is not hard to prove. All right, so f, let's see, now let me just call it, yeah, since I have a lot of stuff inside this D, okay, it's a little bit clearer, I think, if I use that capital D notation. But okay, what's the definition of the derivative? It's the limit as x approaches a, I guess I'm using the x approaches a one here. I'll try to switch back and forth. F of x plus g of x minus f of a plus g of a over x minus a. Okay, that's the definition of the derivative of the sum function f plus g. Okay, so we go back to our definition. And now, let's see, I'm going to work on that expression inside the limit using the algebra that we have. I can rewrite the expression inside the limit as f of x minus f of a minus, no, plus g of x minus g of a. Just rearranging terms in the numerator. Okay. Because remember, this minus here applies to that g of a as well as to f of a. So that was just algebra. And now I can write what's now inside the limit, that expression, as the sum of two expressions. Break it up into a sum. And this is just using algebra. So I make, from one big fraction, I make the sum of two smaller fractions. Okay, and now I'm going to use the limit laws. We talked about, a while back now, and that you have, there's a handout on the limit laws posted on Blackboard with the list of all of those. This is the one that says if I have the limit of the sum of two things, I can break it into the sum of the limits. Well, assuming that all the limits involved exist. Okay. Well, now I'm down to this, which is the definition of f prime of a. And then this limit, that is the definition of g prime at a. Okay, so, all right, and that means I made a mistake right there, and because I should have called that a. A is the fixed number, x is the number that's getting close to a. So that should be that. Okay. Okay, so we've proven it then. The derivative of f of a plus g of a, or sometimes you could write it like this too, f plus g at a is equal to f prime at a plus g prime at a. Or in other words, if I put now x in for a, okay, so now x, I'm not taking one of these x's, I'm just taking a real number x. This really says that the derivative of f of x plus g of x is f prime of x plus g prime of x. So that proves it. It follows this rule, and mathematicians put this whenever they're finished with a proof. Okay, this proves this statement that to get the derivative of the sum of two functions, all I've got to do is to add the derivatives of the individual functions. Okay, let's apply this to a problem. Okay, before I do that, are there any questions? Oh, I should just do 2 at first, so let me erase that. Okay, so suppose I have h of x equal to 3x squared plus 6. So I've got the sum of this function and the sum of that function. That's 3 times a polynomial. That one is. That's just a constant function. From what we just learned, h prime of x is the derivative of 3x squared plus the derivative of the function 6. Okay, so that's what that rule gives us. Well, we learned how to differentiate constant times a function yesterday. I've got a constant times x squared inside that first expression. So the last thing we proved, you can pull the constant out. And the derivative of 6, that's a constant function. That's 0. Okay, and then the derivative of x squared, well, that goes back to the rule about f of x equal to x to the n, and the derivative being n x to the n minus 1. So this derivative of x squared is 2x to the 2 minus 1 is 6x. Any questions? Okay.
Excuse me, miss. I have a question.
Yeah.
Where do you get the 0? I mean,
The
yeah, how
0,
do you
but
get it?
from because 6 is a constant function.
Okay.
So we get it from this rule.
Oh, okay. I got it.
Okay. Anybody
thanks.
else?
Thanks.
Oh, you're welcome. Let's do one more. Let's see, what shall I call this function? H of x. Okay, well, that's the sum of three functions. But if the rule works for two functions, the sum of two functions, it works for the sum of three functions too, and I'll show you why. Okay, so I want the derivative of, okay, different color, okay. H prime of x is, well, I can group h of x into the sum of those two functions. Okay, so it's the derivative of x to the fourth plus the square root of x plus the derivative of 1 over x from the rule that we just proved was true. Sum of two things. But now, inside that first d, that's the sum of two functions. So I can use the rule again. So now it's a derivative of x to the fourth plus the derivative of the square root of x plus the derivative of 1 over x. Okay. So you can apply it, the rule, to the sum of n functions, or as many functions as you want. You can't take the sum of an infinite number of functions, however. That gets into something you talk about in second semester calculus, but you need to make sense of that. But okay, for a finite sum of functions, the derivative of that finite sum is the sum of the derivatives. Okay, so we're not finished. Now we are going to use the power rule. The derivative of x to the fourth is 4x cubed. The derivative, okay, before I take the derivative of the square root of x, I need to write it a different way. I need to write it as x to the 1/2. And I also need to write 1 over x in a different way. I can write 1 over x as x to the -1. That's just using the rules of algebra, which you need to be up on those if you are not. Okay. I'm assuming you know the rules of algebra. It's a prerequisite. Okay, so let's finish. So we got 4x cubed. And then this one, okay, this is again a function of the form x to the n. So the derivative is 1/2 x to the -1/2. And this is a function of the form x to the n. And here n is -1. So its derivative is -1 x to the -1. So finally, that's a 1. 4x cubed plus 1/2 x to the -1/2 minus x to the -2. There's the derivative. Any questions? Okay. Then let's see. Well, actually, I'm going to write this next thing as a rule, but it follows from rule number 4 and rule number 3. But let's write it down anyway. So we are up to 5. This would be rule 5. Okay, the derivative of the difference of two functions is just the difference of the derivatives. Okay, I guess don't always put the parentheses there. I use parentheses to help avoid confusion about what I'm talking about. So it's kind of important here because I'm talking about not just the derivative of f and then minus g. I'm talking about the derivative of f minus g. Okay, but well, this just follows from Rule 3 and Rule 4. Because f of x minus g of x is equal to f of x plus minus 1 times g of x. Okay, that's from algebra. Okay. And if I write f of x minus g of x like that, okay, then the derivative of f of x minus g of x is equal to the derivative of f of x plus minus 1 times g of x. And now I can use Rule 4 to say that this, is equal to the derivative of f of x plus the derivative of minus 1 times g of x, because I have a sum of two functions there, okay? So I might make a note here. This is rule number 4. But then I can use rule number 3 on this and pull out that minus 1, because that minus 1 is just a constant. So this is equal to, I'm going to be using number 3, the derivative of f of x plus, pull out the minus 1, the derivative of g of x. And I guess, so that's just f prime of x plus minus 1 times g prime of x. But then using algebra, that's what you mean when you write f prime minus g prime. So that proves it. Okay, that's supposed to be a period. So yeah, this rule follows from Rule 3 and Rule 4. Okay, so we are up to 6, right? Question?
I didn't have a question, but I think there's some people in the waiting room.
Oh, thank you. Thank you for pointing that out. Okay. Okay, I'm going to keep working on how to make you a co-host, Mr. Miller, and that would really help. Okay, so share content. Okay, screen. All right, so back to this. Okay. Well, what about the derivative of a product of two functions? And okay, what might you hope that, if you have the sum of two functions, the derivative of the sum is the sum of the derivatives. You might hope that if you have a product of two functions, it would be the product of the derivatives. Okay, well, that doesn't work, and I'll show you why. It's not equal to f prime times g prime. And example, it just flat out doesn't work, because suppose I take f of x, or let's call it h of x. H of x equal to x to the 5th. Okay. Well, x to the 5th, using algebra, I can write that as x squared times x cubed. So I can write x to the fifth as the product of two functions. So if I let f of x equal to x squared and g of x equal to x cubed, then, okay, h of x is the product of f of x times g of x. All right, but what's the derivative of h of x? Use the power rule. That's 5x to the fourth from what we've learned. I guess that was rule number 2. And okay, the derivative of f of x is the derivative of x squared. And again, using rule number 2, that's 2x. The derivative of g of x, well, that's the derivative of x cubed, and that's 3x squared. Okay. So the derivative of, let me just write it as, so this is f prime of x, that's g prime of x, and this one is h prime of x. And so h prime of x, oops, is equal to 5x to the fourth. F prime of x times g prime of x is equal to 2x times 3x squared is equal to 6x cubed. These two are not equal. All right, so taking the derivative of our product is more complicated than just taking the product of the derivatives. And just to be absolutely clear, this does not work. Exclamation, exclamation, exclamation. So what does work? Okay. Oops, nope. Okay. So here we go, 6. The derivative of the product of two functions is equal to f prime, f times g's, f prime of x times g of x plus f of x times g prime of x. That's the rule. And we're going to prove that. But all right, let's check it with this example that we just had. All right. Verify with the last example. Verify just means that I'm going to show it for one case. When I say I'm going to prove it, I'm going to mean I prove it for all cases. So we had x to the fifth is equal to x squared times x cubed. That was what we called h of x. And x squared was f of x. X cubed was g of x. And we know h prime of x by rule number 2 is 5x to the fourth. If I take, okay, the derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. That's equal to, okay, well, f prime of x was 2x. g of x unchanged, f of x, x squared, g prime of x, 3x squared. And now we get 2x to the fourth plus 3x to the fourth is equal to 5x to the fourth. Now we get the same thing on both sides. Okay. So that's verification that this is what you call the product rule. And you're going to want to really learn that. Okay, but let's prove it in general. That was just an example. So now proof. And okay, I'm going to use the x approaches a definition again, just because, well, there's a little bit less writing. So let's see, I want the derivative of f of a times g of a. Okay, so that the product of two functions. Well, the definition of derivative says that's the limit as x approaches a. Notice how I keep going back to the definition. This is what mathematicians do. When you're in a new situation and you go back to your definition says exactly what you mean, not too much, not too little. And learning how to do this, well, it takes some doing. But if you're a math major, you'll be starting that process when you take 3322. Okay, the definition says that this derivative is f of x times g of x minus f of a times g of a. Limit as x approaches a of all of that over x minus a. Okay. And now I'm going to do something, okay, a little sneaky, but allowed. As long as you stay within the rules, you can do anything you want. I'm going to stay within the rules of algebra here. This is the limit as x approaches a of, okay, oops, f of x times g of x minus, okay, f of x times g of a plus f of x times g of a minus f of a times g of a over x minus a. So what did I do there? I added and subtracted something in the numerator, okay? This thing. Now, why would I want to do that? Well, I'm thinking ahead, actually. But notice I did not change anything because I subtracted this number and then I added it back. That's 0. So I have not changed this expression at all. I have just written it in a different form. I'm allowed to do that. Okay, so how does that help me? Well, I'm going to break up this limit again, legally, using the rules of algebra. I'm going to break it up. First two terms. Okay. And then the second two terms, I'm grouping them. Kind of running out of space there. And okay, now using the limit laws, well, I can write, first of all, I can write that big fraction as the sum of two fractions. So let's do that first. So that's f of x times g of x minus f of x times g of a all over x minus a. And then I write smaller. Okay, so now I have that expression written as the sum of two fractions. Okay, and notice, all right, let's see. Let's try using that. This expression is the same as this expression. I just wrote the first one and the second one in a slightly different way. And the second one is the same as this one. I'm just using the rules of algebra so far, okay? Those three green things are all the same expression, just written in different ways. Now I can use my limit laws to break this limit of the sum of two things into the sum of two limits. Yeah, I probably should have left more room. I'm going to squeeze it in here. Okay, f of x, g of a, minus f of a, g of a, all over x minus a. Okay. Let's put this equal way over here. Okay, so what can I do next? Well, I'm going to do some algebra on this, and then I'm going to use limit laws again, but let's do the algebra first. Yeah, the first term here, this one, has an f of x in both terms on the top, so I can factor an f of x out of that. In the second limit, I have a g of a in both terms. I can factor a g of a out of that. So this is the limit as x approaches a of f of x times g of x minus g of a. And I'm going to write the x minus a with that. Okay. I can put that denominator here, or I can put it under f, or I can put it under the whole thing. It doesn't make any difference algebraically. And then I'm going to do the same thing over here. Factoring out the g of a. And rewrite those expressions in that form. That's just algebra. Again, algebra going from here to here, just algebra. Now I'm going to use the limit laws again. Okay, I'm going to break, oh, I need the marker again, make it blue. I'm going to break this into the product of two limits, and I'm going to break this into the product of two limits. Okay, using the limit laws. So this is the limit as x approaches a of f of x times the limit as x approaches a of g of x minus g of a over x minus a plus the limit as x approaches a, whoops, looks like a g, of g of a times the limit as x approaches a of f of x minus f of a over x minus a. Okay, And I hope you're seeing some things now. What is this thing equal to?
Zero.
No.
It was just a shot in the dark.
Oh, okay. No, try again.
Is that G prime of A?
Yes. Yes. That's the definition of G prime of A. Okay. So what I've got now, another equal sign. This is G prime at, whoops, it's the wrong place. This is G prime at A. And of course I've got this, and I've got this. And what's this thing equal to?
The next one will be equal to f prime of A.
Yes. And that leaves this limit and that limit. Well, G of A, A's this fixed number. So G of A is just a constant. Okay. So its limit is G of A. And what's this limit? X approaches A of f of x.
Want to be f of A?
Yes. Yeah. Before you can talk about the derivative of f of A times G of A, f prime of A and G prime of A must exist. Okay. And if f prime of A exists and G prime of A exists, f has to be continuous at A. So that means you can use direct substitution. Okay. And I haven't really talked about that yet. But if a function is differentiable at a number, it is automatically continuous at that number. So saying it's got a derivative is saying something else. But there we have it. Okay, so the derivative of f of A times G of A is equal to f of A times G prime of A plus, I'm going to write it in a slightly different order, f prime of A times G of A. And so if I put in x in the place of A, get kind of used to seeing x as your variable. You have to keep in mind when you're going through different things, what each letter represents. Right now, x is just a number. Oops, that's not plus. It's times. X is just a number and A is just a number. So there it is. The product rule follows. And we have actually proven that the product rule works. Okay. So that's an actual mathematical proof. This is an example. Okay. Well, any questions before I work an example of this? I did one already, actually. I could do some more. Kind of helps to work some problems as you go so you can absorb it more easily.
All right. Before you start, there was somebody in the waiting room.
Okay, thank you. Let's go back. Let's make sure it's not for my next class. Well, I'll admit him. Okay, I'm not sure. If I were seeing
Yeah,
you
I'm
in
not.
person,
You might have gotten
okay,
like that.
if I were seeing you in person, I would know all of your names and your faces by now, but I can't see most of you in person. Now, when you're taking the exam, I'm going to require that I be able to see you in person. Okay, so if you don't have a camera on your computer, well, you can buy one pretty cheaply, and use that, or you could go to the university and use one of their computers. But on the exam next week, we're gonna do a practice run. I think we said Tuesday. Yours will be, the actual exam will be on Friday. I want to be able to see you when you're taking the exam. So that means you must have a video camera. Okay. Well, let's find the derivative of,
Oh, we can't see the screen.
oh yes, because I didn't do it properly. I'll get trained at some point. Okay. Okay, how about, oh, can't make it too complicated yet because we don't know enough rules yet. Well, let's do this. Okay, let's take that function. So, well, all right. Before you can take the derivative of a root function, you need to change it to exponential notation. But I'm thinking of this as being the product of this function and that function. So it's the derivative of x to the 1/2 times, and the cube root of x, that's x to the 1/3. And the fourth root of x is x to the 1/4. Okay. So I do have the product of two functions here. So let's just give them names. Then f prime of x, using rule number 2, the power rule, is 1/2 x to the minus 1/2, and g prime of x, well, that's the sum of two functions. So we'll have to use what we proved that today. That was number 4, I think, number 4 and number 2. This is the derivative of x to the 1/3 plus the derivative of x to the 1/4. So that's writing the sum, the derivative of the sum as the sum of the derivatives. That's rule number 4. And then the derivative of x to the 1/3 is 1/3. That's a 1. 1/3 minus 1 is minus 2/3. And then x to the 1/4, that would be 1/4 x to the 1/4 minus 1 would be minus 3/4. Okay, so that says that the derivative of the square root of x times the cube root of x plus the fourth root of x is equal to f prime times g plus f times g prime, and f prime is 1/3 x to the minus 2/3. G was x to the 1/3 plus x to the 1/4. And then f of x was x to the 1/2.
Isn't that to f prime?
Oh, you're right. Right. Okay, let me go back and change that. Yeah, I looked at the wrong thing. F prime is right there. Okay, so that's 1/2 x to the minus 1/2. Whoops. Okay, that's a little smeary. Okay, yes, thank you for that correction. Okay, so then I've got x to the 1/2 times, and times this. Okay, so that's 1/3 x to the minus 2/3 Okay, now, so I've got this, that's the derivative. All right. Well, not for tomorrow, but, and not next week, but for the next week's homework, you're going to have to do a lot of derivatives now using the differentiation rules. Okay. Tomorrow, no. In 2 weeks, your homework will require you to use the differentiation rules. Because believe me, you would not want to use the limit definition to figure out what that derivative is. That would be a nightmare. But yeah, by breaking these into rules about different combinations of functions, you don't have to. It's a shortcut. And now I've got this big algebraic expression, which I can simplify. But for week after next, I want you to concentrate on using the rules correctly. We'll worry about simplifying the week after that, okay? But I may as well clean it up. So right now, I want you to focus on that piece, and that is an answer, okay? Oh, but I can clean it up. Well, it's still going to be pretty messy, I guess, but let's see what we get. Okay, if I multiply this out, so I've got 1/2, and then I've got x to the minus 1/2 times x to the 1/3 plus 1/2 x to the minus 1/2. Oh, I'm running out of time fast. Okay, x to the 1/4 plus, let me just finish this quickly, x to the 1/2 times x to the minus 2/3 plus 1/4 x to the 1/2 times x to the minus 3/4. And I can write that as, well, the rule, if you have x to the a times x to the b, that's equal to x to the a plus b. So minus 1/2 plus 1/3 is minus 1/6. And then same rule, minus 1/2 plus 1/4 is minus 1/4. And then same rule, 1/2 minus 2/3, that's 3/6 minus 4/6 is minus 1/6. And then 1/4, and then 1/2 minus 3/4, that's 6/12 minus 9/12 is minus 3/12, which is minus 1/4. So if we take it one step further and combine those two, that would be 5/6 x to the minus 1/6, and then 3/4 x to the minus 1/4. So there's your answer in a simplified form somewhat. But okay, this is the derivative, even though it's kind of messy, complicated. This is a derivative cleaned up. They are both equal to the derivative. Okay, well, that leaves me, well, 1 minute. So, well, any questions before we close? Any questions about this problem?
Nothing on this, but I do actually have a question about number 2. Rule of the
No.
homework.
Okay.
I'm sorry, but I have tried it every way we could use it, and I've gotten nothing but 0/0.
You don't get 0/0. Okay. The rest of you can go. Okay. Class is over. Let me explain why it's not 0/0. Okay. So number 2, you want to find f of x. F of x is 37. You want to find f prime of x. With the definition. Okay, only. Okay, so definition says that's the limit as h goes to 0 of f of 37. No, sorry. F of x plus h minus f of x over h. Yeah, that's the definition, right?
Mm-hmm.
Okay.
And when you put in the numbers, it becomes 37 minus 37 all over
Yeah.
h.
Yes.
37 minus 37 is 0, and when you factor in the h, it becomes 0 over 0.
Ah, no. Okay. You now have the 0. Yeah. Let me get the 37 minus 37 is 0. But h is not 0. As
Oh.
long as I've got that limit out there, h can't be 0.
Okay.
Okay. Well, now I have, what's 0 over 1 equal to? 0. What's 0 over 0.5 equal to?
0.
0. 0 over h, as long as h is not 0, is 0.
Oh, no wonder I couldn't figure it out.
Yeah, it's so easy, it's almost hard. All right. Okay, but yeah, you have to remember, as long as you have this, h cannot be equal to 0, and that means that this number is 0. And so you're looking at the limit of a constant.
Okay, thank you for that. I never would have figured that out.
I kind of struggled with that when I was a kid too. Okay, okay,
Thank
okay.
you.
You're
Thank you so
welcome.
much.
Let's see. Anybody else got questions?